Hey folks, Matt Easton here, Scholar Gladiatore. So really simple video. I'm holding a small sword here, but I could be holding various other types of sword. And this is really a simple video to reiterate a point I've made in previous videos, and I'll keep it fairly short. And that is that material science, in other words, what you're able to make in terms of the material, the steel in this case, and the way that you're able to heat treat that steel, your science, your mastery of science has a huge effect on the weapons that you make. And very often I think when we're looking at weapon design, particularly I think people in HEMA are particularly guilty of this, we tend to look at things purely out of the eyes of function and how effective something is. So, which cuts better, which is, which kind of is best for parrying or thrusting, or which is better for thrusting through mail and which is better for cutting through bone and this kind of stuff, or cutting through a gambeson. So we tend to break it down into very physical, mechanical causes and effects, as it were, the kind of what the weapon does and how to make it more effective at what it does. But the fact is that what you can do in life is very much dictated by what you have available to you. Okay, if you want to build a skyscraper, but you only have stone, then you're gonna have some trouble. Okay, if you want to build a bow, but you live in a desert and there are no trees, you're going to face some problems. Okay, so you're looking at an Eskimo bow and go, which is better, Eskimo bow or samurai bow? Well, kind of unfair comparison, because kind of the Eskimo bows, they have access to animal parts, basically, maybe a bit of driftwood occasionally, but essentially bits of bone and horn and sinew and ivory and tooth and stuff like this, okay, because that's what's available to them. Whereas if you look at you go to Japan, well, they've got basically everything available to them, from bamboo to various types of wood to obviously steel and things like that. But equally, then if we go to the English longbow, well, clearly they've got yew wood available to them, mostly the best being usually from the Alps or the Pyrenees, so mountain yew, but equally you've got yew in England as well, and all over Britain. So the fact is that the materials you have available to you largely affect what you can build. And let's not even get into, there's a whole other topic about durability and, with bows particularly, certain types of bows, composite bows that are made of glued together things, probably don't work very well in very cold and wet environments and stuff like this. Longbows are probably better, but that's a whole different topic. But coming back to swords, so the steel that you have available does dictate the type of blade you make. And that goes for all swords and all weapons, but let's focus just on swords because that's what we like to do on this channel. All swords throughout history. So quite simply, if we limit this to Europe, we could talk about Japanese swords and their design and the necessities of the types of metals that they're working with, types of steel that they're working with. Or we could look at Filipino weapons and the limitations there. But instead, let's look at European weapons. Now, there is a fundamental difference that occurs in the 18th century in Europe. And that is the move from bloomery steel to cast steel. Okay, and what does that mean? Well, let's call cast steel crucible steel, which is essentially, a lot of you will have heard about woots and crucible steel from an earlier and contemporary period, but mostly associated with India and the Middle East. Well, one of the main mechanical reasons for there being an advantage to cast steel, in other words, it's been liquefied and then solidified again in various forms. Let's not get into the technology of how, because that can be done in various ways, but it's been liquefied, the crap skimmed off, what we generally call slag, okay? So slag skimmed off, and then it's been solidified, and you end up with a homogeneous, good piece of steel that you can introduce the impurities you want in the amounts that you want. So if you melt a thing and you end up with pure iron, you can now introduce the exact amount of carbon you want. So if you take it to pure iron, near enough to pure iron, then you can introduce your 0.9% of carbon into it and you end up with 1090 steel, more or less. Okay, you can introduce a little bit of nickel or a little bit of chrome or a little bit of vanadium, a little bit of manganese, whatever you want to put in there, sulfur, phosphorus, all these other things you commonly find in steel. Steel is an alloy, just to remind any of you. Iron is the element, and you introduce the impurities into it in the amounts that you want to get the steel that you want. If we look at Wilkinson Swords steel, for example, in the 19th century, they had steel specifically made for them by a factory in Sheffield, which was the main steel making centre of England at the time, to their exact specification with very small tolerances. And the steel that Wilkinson swords were made of was roughly equivalent to a modern 1095 steel. Now, how does this relate to how I started this video? Well, quite simply, in the 18th century, it was possible to make small swords, sabres, various other types of sword that were around at that time from cast steel. That is, steel that is produced from iron which has been melted, and then the correct impurities, the correct percentages of impurities reintroduced back into the metal. Before that, it wasn't that simple in Europe, okay? Whilst crucible steel did exist in the Middle East and India, it didn't by and large exist in Europe. There are a few exceptions. Wootz was occasionally imported into Europe. Debatably, the Ulfbert swords from the sort of 10th century thereabouts were made of crucible steel. But I'm not going to get into that because that's slightly more contentious and complicated. But generally speaking, most swords in Europe in the Middle Ages were made of bloomery steel. Now, the bloomery steel production process, by its very nature, keeps a lot of the impurities in the steel and introduces others as well. So you end up with a lot of slag. Now, what is slag? A slag is essentially it's a bit like a ceramic type mixture of impurities that are in the steel. They're literally in the steel. So for anybody who watches Forged in Fire, for example, they'll sometimes refer to inclusions. Well, inclusions is a general term that can refer to lots of things. But if you think about your if you imagine a piece of Play-Doh or plasticine, and it's a red piece of Play-Doh or plasticine, but some kid or one of your friends has got some blue bits, and when you roll it out, you can see some little streaks and bits and dots of blue bits in the red. That's like inclusions in bloomery steel. Now, why are inclusions bad? Well, ironically, depending on what they're made of exactly, an inclusion can actually be harder than the steel around it, but also brittle. But the point is that when you don't have a homogeneous material, when that material comes under any sorts of stresses and strains, it's going to be a focal point for magnifying the chance of breaking at that point. It essentially means that the bits of metal around it are not stuck together. It's a bit like having a bubble inside a piece of concrete or plastic or something. It's something that's in there, and it's making the material solid or seems solid, but it's not part of, it's not bonded with the material around it. So it's really a source for failure. Now, how this affects the manufacture of sword blades is hugely, quite frankly. So one of the reasons that pattern welded blades were made the way they were is because the twisting and the patterns that you end up with are representative of what you've done, the folding and twisting and all of this kind of stuff that spreads out those risks and also reduces the chances of having fractures go in straight lines from any individual piece of inclusion or slag. So essentially what you're doing is you're creating a structure a bit like a rope or a cable inside the metal. So it makes it more difficult for that thing to break apart because of any bad bit that's in part of the blade. With a monosteel blade, if you've got a big piece of slag in it, then you're going to get a fracture more likely at that point when the blade comes under a sudden shock or flexing or this kind of thing. So, in the 17th century, in the 16th and 17th century, the production of steel improved such that the impurities, the slag inclusions, were generally speaking being able to be reduced. And it is notable that this is the same period that we start to get more slender blades. Now, many of you will have noticed that if you look at medieval swords, I'll just grab a longsword from behind you, they are very often, this is from Dynasty Forge, this longsword, and I will be reviewing it, they are very often relatively narrow at the centre of percussion and relatively broad at the base of the blade. Now, I'm not going to say that this is only for this reason, it's not, it's for many reasons. But fundamentally, it is very largely related to strength. Okay, when you're hitting someone with that portion of the blade, that width there is the important part. How wide the blade is here is not really important. I could bring that blade down to being the same width as here, and it would still strike with almost the same amount of energy as having a broad base here. Now you would say, oh, but Matt, the total mass is higher, so therefore, well, yes, that's true. The total mass is higher, but I'm not hitting them with the back end of the sword. I'm hitting them with the end of the sword. So we're actually talking about rotational momentum here. So actually it's the mass up here which actually gives how much energy the blade strikes with. That's why something like a falchion or a machete or a Chinese dao hits with more force than a narrower ended sword like a rapier or some types of long sword or a Chinese jan or whatever. So quite simply, one of the reasons that the blade is so wide at the base here is for strength. Okay. Now we can say, I think with a fair degree of confidence, that blades that were narrow at the base as well as narrow up here, because we've had blades that have been narrow up here for a lot of history, but blades that are narrow at the base, you need to have a lot of faith in your steel. You need to have a lot of faith both in the quality of the steel and the heat treatment. Well, those two things are interconnected, because if you know more about your steel, then you can learn more about the heat treatment of it. If you're able to more precisely produce a similar type of steel time and time and time again. Remember, in the modern world, we just go and buy some 1065, 1075, 1095, whatever. If we know what it is, but they didn't. Okay, if you're able to get steel which is more the same every time, you can perfect your heat treatment. So those two things are connected. So in the 16th and 17th centuries, we start to see blades get narrower at the base of the blade. They don't necessarily get narrow up here, because you'll notice long swords of the 14th, 15th century, and one-handed swords as well, of course, are already quite narrow up here. There are rapiers which are this sort of width, and certainly side swords which are this sort of width all the way along, but they tend to be much narrower at the base of the blade. And my belief, and I think all the evidence supports this, is that one of the reasons for that is the material science. The steel was getting better, more regulated, more understood, and therefore the heat treatment as well, which enabled them to make blades which are getting lighter, and or they could keep the weight the same and make them longer. And we absolutely see in the 16th and 17th centuries, blades do generally get narrower at the base and longer. So they're not necessarily getting lighter, because a rapier is about the same weight as a medieval arming sword, but they're a lot longer. So what they did was, well, I can happily handle a 1200 gram sword, but you tell me, you the sword maker, you tell me that you can now make my blade narrower down here, saving some weight. Well, hold on, I can handle 1200 grams, so why don't you just make the blade narrower down here and add 6 inches to the length? And the sword maker goes, yeah, I can do that. So, and we have to add on to that as well, understanding of blade geometry and blade shapes, and just the skill, the inherited skill, the master to apprentice system of improving understanding of how to make good blades. Also, almost certainly played a part in that as well. So to conclude there, I've whittled on for quite long enough, I think, which I didn't intend to do, but that's common with me if you're on this channel. And if you're not subscribed, please go and hit that subscribe button. I sometimes say interesting things, I hope. I think that material science, the quality of the steel, plays a very large part on the shape of the blade. And when we look at medieval swords, we're so used to seeing blades that are broad at the base, and this is actually a fairly narrow one, but if you think about Viking era swords, or you look at the really broad at the base, kind of type 18 and type 15 type blades, which are really sometimes very broad at the base, You think, well, why? Why is all the width down there when you're hitting someone with this bit up here? Part of it is undoubtedly about how the total weight of the weapon and the balance and all of that kind of stuff. But generally speaking, you look at later period swords, you look at other cultured swords, whether it's Japan or China, that's not something you find very much. I think a very large part of why we get blades which are so broad at the base is to do with the strength that they wanted out of their weapon. They wanted to minimise the chances of them breaking. And the fact is, we know from medieval artwork that swords did break a lot, and we read it in texts as well. And part of the reason for that is slag. So there we go. The reduction in slag and then the move in the 18th century really to cast steel really changed a lot. So don't think that just because a blade is narrower at the base that it is somehow a less powerful blade. If we take something like this, is actually an 18th century blade mounted on a saber hilt, but that is actually broader at the centre of percussion than the medieval style longsword. Okay, so just because a sword is narrower at the base doesn't mean that it's necessarily going to hit with less authority. And just a final piece of anecdotal evidence in terms of cutting tatami mats or pumpkins that I did recently, or water bottles or whatever, we often find that blades which are narrow down here cut just as well as these broad based medieval swords. It's more to do, the cutting capacity is more to do with the edge geometry and the width at the centre of percussion. The base of the blade, not so much. Anyway, I hope that's been somewhat interesting. Feel free to, I'm sure that some of my science is not explained exactly right, but the fundamentals are the less slag you have in a blade, the more reliable the steel is, therefore the more reliable the heat treatment is, therefore you can make narrower blades. And quite simply, in the medieval period, they could not have made reliable small swords. By the 17th century, they could. This type of blade you can only make with good, practically modern quality steel, and they didn't have that in the medieval period, with a few exceptions. Cheers folks! Thanks for watching. We've got extra videos on Patreon. Please give our Facebook a like and subscribe if you haven't already. Cheers folks!